All right, I'm actually pretty excited about this video. It is going to be the first in a series of videos that demystifies, or I'm going to call it a boot camp for limits. Boot camp for limits. So let me show you the list of topics I'm going to do. This video is going to be what is a limit. You can read all those. So there's lots of different topics. I thought about doing a giant video, and then I thought, it might be easier for myself, honestly, to just go ahead and put this in a bunch of shorter videos, and I'll just put it together in a playlist for you. So you can do the entire chapter in either your AP Calculus, regular honors calculus, or maybe business calculus class, all about limits. All right, I think I'm going to hit it all here. I'll be using a textbook to kind of guide myself to make sure I hit all the important aspects of this. I'm also going to post a PDF of this document for each of my videos linked through YouTube onto my website. So if you want to download it and take notes, you are welcome to do that. I hope this really helps a lot of students out there. I do a lot of tutoring, and certainly limits are an item of confusion and a little angst and anxiety. So I'm hoping by doing a series of videos that I can clear up things for at least some students out there. All right, you ready to dig in? Let's answer the question, what is a limit today in this video? All right, so what is a limit? A limit is a description of what a function is approaching. And when I say what, I mean outputs. Outputs. What is the, because I think of functions as like these little machines that are just spitting out numbers all the time. You shove x in and what comes out? Y, right? Or f of x. So, for example, you can see this drawing that I created here for you. It goes up, it goes down. It's got this little hole in it, a missing element there, and then it goes down like that. So functions are about what you're approaching, not where you actually are when you get there, by the way, and I'll talk more about that in a second. So let's start here. This is hopefully an easy one for you. As x is approaching 3, what are the y values approaching? I mean, you could look at the table, right? I don't have a table here, but you could imagine it. As this graph is peaking at x equals -3, what are we getting close to on the output end of things? We're getting close to 4. So we would say the limit at x equals 3 is 4, because we're approaching it from both sides, by the way, and I'll talk about that specifically in a future video. But for right now, all you have to know is we're approaching the number 4, the output value of 4, at x equals -3. Now, coming from this direction, as we approach x equals -5, what is our output approaching? Looks like we're heading for the ground, aren't we? We're heading for y equals 0. So the limit at x equals -5, we would say, is 0. All right, so I put this little tricky spot here on there. As x is approaching 0 from either side, you see, as x approaches 0, what is our y approaching? Like if we're looking at the tables here, our table here, our y value would be 3, 2.5, 2, 1.5, right? 1, 1.25. As we're getting closer to 0, what are the outputs getting close to? It sure looks like they're heading toward 1, isn't it? They are. And from the other side, same thing. As I count down from the right here, as x equals 2, y is 2. At x equals 1, y is, 1.5. At x equals 1/2, y is 1.25. You see how we're approaching 1 from either side. Even though the function doesn't exist there, the limit does. The limit at x equals 0 is 1. Now let me show you the notation for this. So the general notation is the limit as x approaches, we typically call a, so that's some x value, on the function that I've shown to you graphically here. We don't have the algebra, we have the graph here, is some value, and we call that the limit. So when you're taking a limit, when you take it to the limit. When you're taking a limit, you're finding a y value. So up above, I said the limit as x approached -3. Do you remember which one that one? That was this one up here. Okay, that was that one up there. As x approached -3 on f of x, didn't mean for that to turn blue, but that's all right. We'll go with it. Is, what did we say? We said 4. The limit as x approached 0, that was the special one. I do have to write f of x each time, by the way, to state which function I'm looking at. I've only got one function here, but I don't know, who knows? You could have two. So what were we approaching as x approached 0? As x approached 0, this function was heading toward y equals 1. Y equals 1. So answers to limits are called values, and they are y values. Hopefully, I've said that enough that you will remember that fact. I guess there was one other that we did here. Limit as x approached -5 on f of x. You remember what that was? That was this guy right here. Our output was approaching 0. Limits are all about what you're approaching, not where you are when you actually arrive. So we were approaching y equals 1. But in the end, it didn't exist there. So take a look at this screen. You might want to pause the video and actually try all of these questions here. You might want to pause the video and try these questions and see what you do here. All right. So let's go through these one at a time. And I know my camera here is a little bit in the way. I guess I didn't plan ahead on that one, but that's all right. You can deal with it. So this is called a function. You see it passes the vertical line test. You would call this a piecewise function. It has lots of pieces. So it has this linear piece over here. It has a different sloped linear piece. It has a linear piece over here, but it also has this weird jump. Like we're heading down there, and then the function literally jumps up there for just a nanosecond, and then it continues along. It skips this right here. We've got this section here that looks like it's some sort of curve, not a line. Okay, so let's go through these answers. Again, I hope you paused the video and just tried these. All right, the answer to this first one, the limit as x approaches 0 is what? Well, it looks like as we're traveling from either direction, doesn't it look like we're heading toward y equals 0? We end up getting there too, right? There's a closed circle here. What about, go to the right there. What is x as x approaches -2? So here's -2. What are our outputs? If we were to look at the t-table or the t-chart, what are they getting close to? They are getting close to the number 4. So the answer up here would be 4. There you go. I can squeeze it in for you. Okay, moving on. Now they get a little trickier. What about -5? -5. As the function approaches x equals -5, I'm going to draw my picture coming from the right there. We're sort of going downhill from the right. It sure looks like the outputs are approaching 2, aren't they? They are approaching 2. So we fill that in. It doesn't matter that it's an open circle. Okay, it's approaching 2. We expect to be at 2, and then we're surprised because we're not there. Okay, all right, moving on. The next one, limit as x approaches 2. All right, this is the one, I did this on purpose because we have to have this conversation. We are heading toward x equals 2. We're on a freight train or we're on a roller coaster coming in both directions here. Don't you think that we would expect to arrive at y equals -4? Yeah, because this is where they converge right here, right? But it's an open circle, and in reality, the function jumps up there. But what's the limit? Which is it? Is it -1 or is it -4? The limit is -4 because that's what we're approaching. Limits are all about what you're approaching, not where you are when you actually get there. Let me jump down here because this is important now. So The limit at x approaches 2 was -4. What is the actual value at f of 2? That's where you read where the closed circle is, and this one is -1. That one is the -1. See, so I did want to draw that distinction there. These two are really important to understand the difference between the two. Limits are what you're approaching, whereas when it just says f of 2, that you look for the closed circle. All right, so we have one more limit here. What is the limit as x approaches 3? Right here. It's an open circle. Does that matter? No, it doesn't matter because we are approaching y equals 0 both from the right and the left, and I'll talk more about that in the next video. What about f of -2? That's where you just literally read where the closed circle is. So up here, f of -2 is 4. And remember, we can write that as an ordered pair, by the way. This is the same as the ordered pair, -2, 4. All right, what about f of 0? F of 0, that was 0. That was this dot right here. And f of 3. That was this open circle here. Does the function exist there? Nope, it does not exist there. So D and E does not exist there. So make sure you check all your answers. Hopefully you got all those right. Okay, there's more to this, so stick with me here. We got this is not a long video, but there are a lot of important topics, and we haven't covered them all yet. Okay, so let's let f of x be a quadratic. What kind of shapes are those? Those are, right? Those are the parabolas. So this is a right shift by 2, and then we have our standard parabola that has, I use what's called the 1, 1, 2, 4, at least what I call it, 3, 9 trick, and I teach my students that too. So we go over to up 4. Again, I don't know why I just switched to red, but I did. And then I can sketch my graph here. So I wanted you to just make the connection that we can be given the algebra, and there's a graph going on in the back of this, right? So let's solve this first limit as x approaches 1. As x approaches 1, here's 1. What is our function approaching? Our function is approaching 1. Does it actually get there? Yeah, there's a closed circle there, right? We just can't see it, but the function exists there. So it would be 1. What would the limit as x approaches 4 be? Well, you can look up here, can't you? And you see it's actually a dot. It's 4, 4. So we would say this approaches 4. Now here's where I'm going to get tricky on you. What about 8? That's off my grid. Can I do that right now? What do I do? Since this function is nice and continuous and just keeps going in a predictable way, there's no jumps or crazy things happening, we can literally plug in x equals 4. We can substitute. We don't have to go to the graph and look at it and everything. We can literally plug in, substitute x equals 4 into this. So down here, we're going to plug in x equals 8. So this would end up being the quantity 8 minus 2, the quantity squared. That would be 6 squared, which is 36. So the value of that limit is 36, and we did it by simple substitution. All right, so I started this video by really making you focus on the graphical understanding of a limit, and now I'm sort of transitioning to include the algebra into this and the numbers and how you can plug those things in. So what about the next one? Why don't you just think about it for a second, maybe pause the video. What about the limit as x approaches -3? What would it be? It would be -3 minus 2 squared. That's -5 squared, which is positive 25. So this graph is going to be approaching positive 25 at x equals -3. We can't see the graph there, but we know that would be the case. All right, so isn't that cool? You can evaluate limits. Really, it's like algebra 1 or pre-algebra again. You just plug the number in and you get your answer. It's like free points on your quiz, folks. Now, of course, there's got to be special scenarios, right? Nothing can ever be easy in math, especially calculus. Limits can fail to exist. Limits can fail to exist. So I've given you a piecewise function. It's got 3 pieces to it. We've got some open circle, closed circles. These are called jumps in the graph, where it jumps. And I'll talk more about that in the next video as well. But I did want to at least begin to introduce non-existent limits here. So the limit as x approaches 3 on this function. Where is 3? 3 is over here. Our function, from the right and from the left side, both are approaching 1. So that one exists. Now what about 5? Well, you see the graph only exists. This function only exists on the left side, and so it's okay. We just look at it coming from this direction. What are we approaching? We're approaching y equals 0 at x equals 5. All right, now here's where the curveballs come in, folks. X approaching 0. As x approaches 0. So let's find 0, and let's see what's happening from this angle and from this angle, from the right and from the left. What are our outputs approaching? Well, this is strange. From one side, we think we're going to approach 2, or we are approaching 2. We think we're going to hit 2. However, from the right, our table of values, if we were to look at it, they're getting really close to 4 as we get close to 0. So what do we say? Well, that's when they don't exist. So we would say the left does not equal the right, and I will formalize that more in the next video. They're called one-sided limits, and we'll talk more about that in a separate video, the next one in my sequence here. The limit as x approaches -2. Does that exist? Here's -2. Well, from the right, we're approaching 0. From the left, we're approaching y equals 2. Remember, values of limits are always y values. So the right does not equal the left. 2 does not equal 0. So we would say does not exist again. Sometimes your teacher wants to support you to support y, that is. So, but let's look at -5. Does the limit at x equals -5, does that exist? Here's -5. The graph only exists on one side. We're going to assume it does not exist over here at all. So this limit does exist. Coming from the one side here, as x approaches -5, we are approaching y equals 2. So that one does exist. All right, you see these special situations here? So you got to watch out for those jumps because the limit doesn't exist there. However, remember this jump back here that I did? This was just a single dot. So the limit from the left here did equal the limit from the right. It didn't matter that the function just for a nanosecond jumped up there. The limits were equal. They were both -4. So that's why the limit as x approached 2 did exist in this example, folks. That's important to understand, and students get that kind of confused. And I get it. It is confusing. But when you have just a little open circle with an oddball point, the limit will exist down here. Whereas on this one, we have a literal jump in the function. Something crazy is going on here. We actually say the function's not continuous there either. All right, we're almost done. We're almost done. I've put together a few extra examples for you, so I want to make sure we go through them. Again, you might want to pause the video and on some scratch paper do these problems. Remember how easy limits are when you can just substitute in. And all 6 of these you can substitute in the x value. Right? There's nothing special going on at that value. So we'll talk more about that later in my sequence when special things could happen. So we can literally put the 2 in there, and of course we get 7. 7, that was easy. Let's go to the right. What do you get when you plug -1 in right here? Don't you get -1 plus 1, which is 0? Oh, well, that makes that easy, doesn't it? 0 to the third is 0. 0 times 5 is 0. This function, if you were to graph it, is approaching y equals 0 at x equals -1. So it must be a left shift by 1 of the whole graph. Don't forget about trig functions. We have to consider those when we're studying calculus. So let's plug in pi. You remember what the sine of pi is? Don't forget the sine function looks like this. It starts at 0, 0, goes like this. It finishes its thing after 2 pi. It's called a period. It does its shape after 2 pi. So here is pi in the middle. What is the sine of pi? It's 0. You see the y value. Here's the y-axis. All right, and it's approaching y equals 0 at x equals pi. Easy peasy. There we go. Let's plug 5 into the next one. I made a rational function here, which can have vertical asymptotes, as you learned in Algebra 2 and reiterated in pre-cal. But are we allowed to plug 5 in? Sure, it doesn't cause a problem in the denominator, right? There's no divide by 0. So we can go ahead and plug 5 in here, and we can plug 5 in here. So we get 10 on the top. We get 2 squared on the bottom, which is 4. So the final answer, we could reduce it to 5/2. So if you were to look at the graph, it's approaching 2.5, 2.5. All right, what about this guy? Can we plug 2 in there? Careful, can we plug 2 in there? Nope, we cannot plug 2 in there because it causes the square root of a negative, and we're going to keep it real here, people. We're not going to Neverland. There's no imaginary numbers here that we're going to work with. So this is not possible. So we would say that this limit does not exist. This is outside the domain. 2 is not part of this domain. The graph doesn't exist there. Remember that this one up here, I said, the graph doesn't exist over here. That's outside the domain. But the limits over there don't exist either. Okay? So in this graph, it's the square root function. It doesn't exist at x equals 2. You go to Desmos, plug it in, and prove to yourself. This limit doesn't exist. All right, this last one. Does this limit exist? Sure, we can plug pi over 2 into both of these. No problem. Right? We remember our unit circle, or I like to just think about the graphs like I did down there, but that's just how my brain works. So remember the sine function. Where's it at? At pi over 2. Here's pi over 2. Where's it at? It's at 1. So the sine of pi over 2 is 1. What about the cosine at pi over 2? Well, let's sketch that real quickly. Do you remember what the cosine looks like? This will be cosine x. Cosine starts up high here, and then it goes down like this, and then it finishes right here. It's the same curve as sine, by the way. Don't forget. You see right there? Here's the sine curve. Cosine has just been moved over a little bit. So I like to think of that as, quote, starting at 1. It bottoms out at -1. Bottoms out at -1. This happens at pi. So where is it at pi over 2? It's at 0. Cosine of pi over 2 is 0. So once again, we get the value of a limit as being 0. Okay, so we've covered what a limit is. I explained it graphically, and then I showed how we can actually solve them out through substitution like in all these. And of course we learned about how limits cannot exist. That's important to understand. And I also showed you that critical moment there where you got to be careful. Just because there's a slight jump in the graph, the limit can still exist there. That answer was -4. All right, so I hope that you check out the rest of my videos in this sequence, and I really hope that they might help you learn about limits, because like I said, I get these questions all the time. So I thought it would be really valuable for me to put together this for you. All right, well, good luck, and I will tell you this. Until next time.